Hello everyone, and welcome to this new video from ControllersTech. In the previous video, we created our very first project in STM32CubeIDE using the CubeMX. We configured the system clock, set up an output pin to control the LED available on the board, and finally wrote a small piece of code to blink the LED at a specific rate so that we could verify everything was working correctly. Today, we will learn how to perform basic debugging in STM32CubeIDE. Debugging is an important skill because it helps us identify and fix errors or unexpected behavior that may occur while the program is running. I will continue using the same project that we created in the previous video of this series. As you can see, the project is already opened and loaded in STM32CubeIDE. To begin, I am going to create a global variable called main_count. A global variable can be accessed from anywhere within the same file, so in this case, we can use it anywhere inside the main.c file without any restriction. Next, I am creating another function. Inside this function, I am declaring a local static variable. This variable will be limited to this function only, meaning it cannot be accessed outside of it. Each time this function is called, this local variable will increase by 1, allowing us to observe how it behaves during execution. Now, inside the while loop, we were blinking the LED in the previous project. In this updated version, I will increment the global variable 2 times, once immediately after turning the LED on, and another time after turning the LED off. This will help us track how many times the loop executes. Finally, I will call the function that we just created so that the local variable inside that function can also be incremented once during each loop cycle. Let's build the project now. The build process completes successfully, and there are no errors in the project. So basically, we now have a simple structure where we are using both a global variable and a local variable. The global variable is incremented inside the while loop, while the local variable is incremented inside the function in which it is declared. This setup will help us clearly understand how each type of variable behaves during debugging. To start debugging the project, click on the bug icon at the top. Since the debug configuration was already created when we worked on the previous project, STM32CubeIDE will directly launch the debugger. If it had not been created earlier, the IDE would first generate a new debug configuration and then start the debugger automatically. We are now inside the debugger. By default, the execution is halted at the HAL init function, which is responsible for initializing the hardware abstraction layer before the rest of the application starts running. On the right side of the debugger window, you can see several different views. These include the variables view, peripherals view, live expressions, registers, and some other useful panels. Each of these helps us monitor different parts of the system, while the code is running. We will explore these sections in detail shortly. We can add breakpoints by simply double-clicking on the left margin next to a line number, or by right-clicking on a line and selecting Toggle Breakpoint. Breakpoints are very useful because they allow us to pause the program execution at a specific line of code so that we can inspect what is happening at that exact moment. For example, I have set a breakpoint at the line where the output pin is set high. When we press the Run button at the top to start the debugger, the program will execute all the statements before this breakpoint and then automatically halt at that line. You can notice that the LED on the board is still off. This is because the statement that turns it on has not yet been executed. The program has paused just before running that instruction. Now, we can use the step into or step over buttons to execute the code one line at a time. For example, if I press step over, this complete statement will be executed, and you can see that the LED turns on immediately. Since this line contains a function call, we also have the option to use step into. When we select step into, the debugger takes us inside the function definition so that we can observe how the code inside that function is executed step by step. Next, we step over the delay function. This means the 500 millisecond delay is executed internally by the microcontroller, and once the delay is complete, the debugger moves to the next line. At this point, the variable main count has been incremented. Then the LED is turned off. After that, we execute the 2-second delay, increment main count again, call the function that we created earlier, and finally the control returns to the beginning of the while loop to repeat the process. If we press the run button again, the program will continue executing. However, it will pause every time it reaches the breakpoint that we set earlier. Now, let's add another breakpoint just before the line where the LED is turned off. With this additional breakpoint, the program will now stop once before turning the LED on and again before turning the LED off during each loop cycle. You can also press the reset button to restart the entire execution from the beginning. When we do this, the control again starts from the HAL init function, just like it did the first time we entered debug mode. I hope you now have a clear understanding of how breakpoints work and how they help us control program execution during debugging. Finally, let's remove these breakpoints by double-clicking on the lines where we added them, so that the program can run continuously without stopping. The variables that we created can be monitored using the Live Expressions window. However, it is important to understand that live expressions only support global variables. It does not work for local variables that are declared inside functions. To use live expressions, you simply need to add the global variable to the window, and the debugger will automatically detect its data type and start displaying its value in real time. Now, let me add a breakpoint just before the line where main count is incremented, and then run the debugger. We have reached the breakpoint, and you can clearly see that the value of main count is still 0 at this point. If we step over this line, the statement will be executed, and you can see that main count increases by 1. I will now add another breakpoint at a later line. When this statement is executed, you can observe that the value of main count becomes 2. This confirms that the variable is incrementing as expected. Now, let's remove these breakpoints and allow the code to run continuously. As the program executes freely, you can see that main count keeps increasing with every iteration of the while loop. Suppose we also want to monitor the value of the local variable created inside the function. If we try to add this local variable to the Live Expressions window, the debugger will fail to evaluate it. The reason is straightforward. The local variable exists only within the scope of its function, so it cannot be accessed globally. However, we can still view the local variable in the Variables tab, but only when the program execution is currently inside that function. Let me add a breakpoint inside the function itself. When the execution stops at this breakpoint, you will notice that the local variable automatically appears in the Variables tab, and at this moment its value is 7. This value is approximately half of main count, which is exactly what we expect. The reason is that main count is incremented twice during each iteration of the while loop, whereas the local variable inside the function is incremented only once per loop cycle. As soon as the execution exits the function, the Variables tab will no longer display the local variable because it is now out of scope and no longer accessible. We can also try to monitor the local variable using the Expressions tab by manually adding it. While the execution is inside the function, its value updates correctly. However, once the program moves outside the function, the variable becomes inaccessible in the Expressions tab as well. So to summarize, global variables can be monitored easily using the Live Expressions window, while local variables can only be viewed in the Variables or Expressions tab, and only when the program execution is within their valid scope. Now, we have already seen how to use the step over option to execute statements one by one. This time, let's use step into on the HAL GPIO write pin function. When we step into this function, the debugger takes us to its actual definition inside the HAL GPIO library. This allows us to go deeper and see exactly how this function is implemented. From here, we can execute each statement one at a time and clearly understand what is happening internally. For example, when the GPIO pin is set, the corresponding value is written to the BSRR register. Similarly, when the pin is reset, another operation is performed on the BSRR register to clear the pin. This is how the microcontroller directly controls the pin state at the register level. We can also observe these internal changes by opening the Special Function Register tab in the debugger. This tab allows us to monitor the actual hardware registers of the STM32 microcontroller in real time. Inside the SFR tab, since we are working with GPIO-A, we need to locate the GPIO registers and expand them. As we are changing the state of an output pin, the effect will be visible in the output data register. Expand the ODR register as well, and then observe the bit corresponding to PA5. When we set the pin, the ODR5 bit changes to 1. This means PA5 is high, and the LED connected to that pin turns on. When we reset the pin, the ODR5 bit changes back to 0. This means PA5 is low, and the LED turns off. You can learn more about these registers by referring to the official reference manual of your STM32 microcontroller. Understanding these registers is very helpful during debugging, as it allows you to verify whether the hardware is behaving exactly as your code expects. So, I hope you now have a clear understanding of how to debug an STM32 microcontroller project. We have covered some basic but very important debugging techniques, which are more than enough for handling small and medium-level projects. In the next video, we will explore how to use the Serial Wire Viewer, SWV, and trace features for more advanced debugging in STM32CubeIDE. That is all for this video. I hope everything was clear and easy to follow. If you have any questions or doubts, feel free to leave them in the comments section. Keep watching, and have a nice day ahead.